BERT, which stands for Bidirectional Encoder Representations from Transformers. BERT is a language model developed by Google in 2018. It is considered one of the most significant breakthroughs in the area of natural language processing. It caused a paradigm shift by introducing a new approach to tackling language understanding tasks, pre-training large corpus of text data, and then fine-tuning for specific tasks, such as question answering and sentiment analysis. This approach has proven to be highly effective and has been the foundation for many subsequent advancements in NLP. Here's an illustration of BERT's pre-training and fine-tuning process, which I will explain in more detail in the following slides. So BERT is built on the transformer architecture, which is a type of neural network that has shown great promise in sequence-to-sequence tasks. Since we have already covered the transformer architecture in a previous lecture, I brief recap its key components. So the transformer consists of an encoder and a decoder, which are composed of multiple layers of self-attention and feed-forward neural networks. The encoder processes the input sequence and generates a sequence of hidden representations, while the decoder generates the output sequence based on the encoder's representations. Following the initial success of the transformer in machine translation tasks, researchers explored using the decoder part of the transformer as a standalone language model. So this led to the development of models like OpenAI's GPT-1, the generative pre-trained uh, transformer, which demonstrate the effectiveness of using the transformer decoder for language modeling. GPT-1, however, was unidirectional, meaning it could only attend to previous tokens in the sequence. This choice is natural for next word predictions, but it also has limitations. So we'll discuss this in more detail in the next slide. So let's compare unidirectional and bidirectional language models. So unidirectional models like GPT-1 build representations of words incrementally based on the words that came before them in the sequence. This means that the representation of each word is influenced only by the words that precede it. While this approach works well for some tasks, it doesn't capture the full context of a word within a sentence. For example, consider the sentence I went to the bank to deposit money. The word bank could refer to a financial institution or the side of a river, and the meaning is determined by the context of the whole sentence. For tasks that require understanding the meaning of a word in the context of the entire sentence, such as question answering or natural language inference, a unidirectional model may struggle. So this is where bidirectional models like BERT come in. So for such models, the representations of each word are built by considering the entire input sequence, both the words that precede and follow the target words. So this allows the model to capture a richer context for each word, which can be beneficial for a wide range of NLP tasks. However, building a bidirectional language model comes with its own set of challenges, which we'll discuss in the next slides. So Elmo, which we discussed before, was one of the first successful attempts at building a bidirectional language model. However, it aggregated the representations from different directions in an isolated manner, which limited its ability to capture complex dependency between words. BERT addressed these limitations by replacing LSTMs with the transformer architecture. In particular, BERT uses the multi-layer transformer encoder to build a deep bidirectional language model, which captures the context of each word by considering every other word in the input sequence. This architecture allows BERT to generate rich contextualized representations of words, which can be used for a wide range of NLP tasks. The BERT input representation consists of three key components: token embeddings, segment embeddings, and position embeddings. Token embeddings are the word embeddings for each token in the input sequence. BERT uses word piece embedding with a vocabulary size of 30,000 tokens. It is a subword tokenization method that allows the model to handle out of vocabulary words and capture morphological variation of words. The input sequence is also augmented with special tokens such as CRS and SEP, which are used to denotate the beginning and separation of sentences, respectively. So the CRS token is particularly important since it is used to generate a fixed size representation of the entire input sequence, which can be used as an input to downstream tasks. Segment embeddings are used to distinguish between different sentences in the input sequence. This allows BERT to handle tasks that involve multiple sentences, such as natural language inference. Finally, position embeddings are added to the token embeddings to capture the position of each token in the input sequence. Different from traditional position embeddings, BERT use learned position embeddings, which are optimized during the pre-training process. So BERT comes in two sizes, BERT base and BERT large. BERT base has 12 transformer layers and 768 hidden units and 12 self-attention heads. So which in total resulting in 110 million parameters. But large, on the other hand, has 24 transformer layers, 1024 hidden units, and 16 self-attention heads, resulting in 340 million parameters. The larger model has been shown to achieve better performance on various NLP tasks, but it also requires more computational resources and longer training times. Back in 2018, BERT Large was considered one of the largest models in the field. However, with the continuous scaling of the language models, we have seen even larger models being developed, such as GPT-3, which has like 175 billion parameters, about 500 times more than the BERT Large. So both models are pre-trained on large corpus of text data, such as Wikipedia and the book corpus, using two unsupervised learning objectives: masked language modeling and next sentence prediction. So the traditional approach to language modeling is to predict the next word in a sequence given the previous words. So why this approach works well for unidirectional language models, it is not suitable for bidirectional models like BERT. So because conditioning on the future words would result in data leakage during pre-training. To address this issue, BERT introduces a new pre-training objective called masked language modeling, MLM. So in MLM, a random subset of the input tokens are masked, and the model is trying to predict the original words based on their context. This allows BERT to capture bidirectional context while pre-training. But the model has to learn to predict the masked words based on both the preceding and the following words. In the original BERT paper, about 15% of the tokens are masked during pre-training. Since the mask token is not present in the input during fine-tuning, which may cause a mismatch between pre-training and fine-tuning. So BERT used the following strategy to handle the mask tokens. 80% of the time, the token is replaced with a mask token. 10% of time, the token is replaced with a random token. 10% of time, the token is left unchanged. So this strategy encouraged the model to learn robust representations of the mask tokens, which can be beneficial for downstream tasks. In addition to masked language modeling, BERT also uses a next sentence prediction NLSP objective during pre-training. In NLSP, the model is trying to predict whether a pair of sentences are consecutive in the original document or not. During pre-training, 50% of the training examples are positive examples, where the second sentence follows the first sentence in the original document, and the 50% are negative examples, where the second sentence is randomly sampled from the corpus. This objective encourages the model to capture relationships between sentences, which can be beneficial for downstream tasks such as question answering and natural language inferences, where understanding the relationship between sentences is crucial. So once pre-trained, BERT can be fine-tuned for specific tasks using supervised learning. The fine-tuning process involves adding a task-specific output layer on top of the pre-trained BERT model and fine-tuning the entire model on a label dataset for a target task. The task-specific output layer can be a single layer or multiple layers, depending on the complexity of the task. In the original BERT paper, the authors demonstrate the effectiveness of fine-tuning BERT on a wide range of NLP tasks, such as sentence pair classification, single sentence classification, question answering, and sequence tagging. The token level tasks, such as question answering and sequence tagging, uses the token level representations from BERT. While sentence level tasks, such as sentence pair classification, use the CRS token representation as the input to the task-specific output layer. So the original BERT paper reported the state-of-the-art results on a wide range of NLP benchmarks, including the GLUE benchmark, which consists of 9 different tasks, such as question answering, natural language inference, and sentiment analysis. BERT achieved significant improvements over previous models on most of the tasks. In particular, BERT large outperformed all other models on the GLUE benchmark, demonstrating the effectiveness of large-scale pre-training for NLP tasks. The success of BERT fundamentally changed the landscape of NLP research and led to the development of many other language models that build on the BERT architecture. So following the success of BERT, several variants have been developed to address its limitations and improve its performance. So here's an illustration of the BERT family tree, which shows the evolution of BERT and its variants. In the next few slides, we'll discuss some of the most notable BERT variants, including Roberta, Alberta, Albert, Electra, and Ernie. So Roberta, which stands for a robustly optimized BERT pre-training approach, is a variant of BERT developed by Facebook AI. It is one of the most widely used BERT variants and has achieved state-of-the-art results on many NLP benchmarks. Roberta builds on the BERT architecture and introduces several modifications to the design and pre-training process of BERT. In addition, it introduces a new pre-training dataset called CC News, which consists 63 million English news articles crawled from the web. The author of Roberta conducted an extensive study to identify the impact of different design choices and the pre-training data on the performance of BERT. They found that by optimizing the pre-training process and the training on a larger dataset, they could achieve significant improvements over the original BERT model. Here are some of the key modifications introduced in Roberta. So I will discuss a few of them in more detail in the following slides. So one of the key difference between Roberta and BERT is the way they handle masked language modeling during pre-training. So in BERT, the masking is performed during the data pre-processing step, which results in a fixed set of mask tokens for each training epoch. To avoid using the same masked tokens for each training epoch, BERT ad hocly duplicates the input data 10 times and masks different tokens in each duplicate. In contrast, Roberta uses dynamic masking, where the masking is generated every time the input is fed into the model during pre-training. This allows Roberta to use different mask tokens for each training epoch, which can be beneficial for learning robust representations of the mask tokens. So the authors of Roberta found that the dynamic masking led to better performance compared to static masking. Multiple studies have questioned the effectiveness of the next sentence prediction objective in BERT. So to investigate the impact of NLSP, the authors of Roberta conducted experiments with different input formats and pre-training objectives. So here are the 4 settings they considered. Segment pair plus NLSP, which is the original BERT input format with the NLSP objective. Each training example consists of a pair of segments which can contain multiple natural sentences. And sentence pair plus NLSP. So each training example consists of a pair of natural sentences, either sampled consecutively from one document or from different documents. And full sentences So each training example consists of natural sentences sampled consecutively from one or more documents up to a maximum length of 512 tokens without the NSP objective. And the doc sentence, so similar to um, full sentence, but the sampling does not cross document boundaries and also without the NSP objective. So the authors found that the NSP objective did not provide significant improvement over the other settings, and in some cases, it even hurt the performance. So they also found that using longer sequence during pre-training, such as full sentence or document level sentence, led to better performance compared to using individual sentence pairs. So based on these findings, Roberta used the full sentence settings without the NSP objective for pre-training. So in addition to the changes in the pre-training objectives and input format, Roberta also introduces several modifications to the pre-training process of BERT. So first, the author found that using larger batch size leads to better perplexity and downstream task performance. Second, the author found that the original BERT is undertrained, and using more data leads to better performance. In addition to the original BERT pre-training data, Roberta used the CC News dataset, which consists of 63 million English news articles. So finally, they also found that the longer training leads to better performance. They trained Roberta for 100,000, 300,000, 500,000 steps. They found that longer training leads to better performance on downstream tasks. Roberta did not show signs of overfitting even after 500,000 steps, which suggests that longer training could be beneficial for large-scale language models. So the modifications introduced in Roberta led to significant improvements over the original BERT model. So Roberta achieved the state-of-the-art on the glue benchmark, surpassing BERT and other language models on most of the tests. So the Albert, so Albert, which stands for a light BERT, is a variant of BERT developed by Google Research. So scaling up language models like BERT to achieve better performance often comes with increased computational cost and memory requirements. Albert addressed this issue by introducing several parameter reduction techniques to make the model more efficient without compromising its effectiveness. The authors show that a configuration of Albert similar to BERT large can have up to 18 times fewer parameters and can be trained up to 1.7 times faster. So there are three key parameter reduction techniques introduced in Albert: factorized embedding parameterization, cross-layer parameter sharing, and inter-sentence coherence loss of sentence order prediction. So I will discuss each of these techniques in more detail in the following slides. So the first parameter reduction techniques introduced in Albert is factorized embedding parameterization. In BERT, the dimension of the token embeddings and the hidden layers are the same, which is a suboptimal design choice. The token embeddings are used to represent the input tokens and only capture the context-free information of the tokens. On the other hand, the hidden layers are used to capture the context-dependent information of the tokens. The power of BERT comes from the hidden layer and not the token embedding. So it is natural that the hidden layers should have a higher dimension than the token embeddings. However, to increase the dimension of the hidden layers, the dimension of the token embeddings must also be increased. This would result in a significant increase in the number of parameters because the vocabulary size is usually very large. So for example, birthplace has a vocabulary size of 30,000 tokens and use 768 dimensional token embeddings, resulting in 23 million parameters. So Albert addressed this issue by by decoupling the dimension of the token embeddings from the dimensions of the hidden layers. So in Albert, the token embeddings are first projected to a lower dimensional space and then project to the higher dimensional space of the hidden layers. This allows Albert to use a higher dimensional hidden layer without significantly increasing the number of parameters. So using this technique, the number of parameters is reduced from like the big O of the V times H to big O of the V times E plus H times E. So where V is the vocabulary size, and H is the hidden layer dimension, and E is the embedding dimension. The second parameter reduction technique introduced in Albert is cross-layer parameter sharing. So in BERT, each layer has its own set of parameters, which results in a large number of parameters. Albert addressed this issue by sharing parameters across layers. There are several ways to share parameters across layers, such as sharing the attention weights, the feed-forward neural network weights, or both. By default, Albert shares all parameters across layers. The authors found that this parameter sharing technique led to significant parameter reduction without compromising the performance of the model uh, significantly. And the third parameter reduction technique introduced is inter-sentence coherent loss or sentence order prediction. So in BERT, the next sentence prediction objective is used to encourage the model to capture relationship between sentences. However, as we discussed earlier, the NLP objective has been shown to be less effective than other pre-training objectives. So Albert introduced a new pre-training objective called the sentence order prediction, which is supposed to be more effective than NLP. So in sentence order prediction, the model is trying to predict whether a pair of sentences are in the correct order or not. The author found that this objective leads to better performance compared to NLP. And actually, this is not a parameter reduction technique, but like to investigate whether the ASP objective is effective or not, similar to what Roberta did. So the parameter reduction techniques introduced in Albert lead to a significant improvement in efficiency without compromising the performance of the model. So it even achieved the state-of-the-art results on the glue benchmark, surpassing BERT, Roberta, and other language models on most of the text. And this performance is quite impressive.